So let's get started, folks. It's sort of the canonical 5 minutes. People are still logging on, but let's just get started so at least we get some momentum here. Before I start, there's a lot of thanks at this moment. Over the weekend, it became apparent that we would likely exceed, our current limits on Zoom, and so we had to scramble to get a webinar with a license that could accommodate what we hope will be the total attendance to this short course. I wanted in particular to call out people who were really well beyond the call of duty. I remember this was transpiring over the weekend where there's no known contract that I know at Cornell that makes people work, with such dedication on that time scale. So in particular, Daniel Haynes, who is basically the boss of CAPE, the Center for Alkaline-Based Energy Solutions, as well as Paul Mutolo. And a particular thank you to Michael Hint, who is the IT person here at Cornell. Also at University of Utah, Shelley Mintier and Katie Snow, who are also instrumental in getting these things off the ground. So with that, let's get started. I'm wearing a jacket just to be formal for 5 seconds. You can see here the Cornell logo, right? This is shameless propaganda. So let's get over that and let's get started. All right. So again, first of all, thanks people for being here. We are spanning 16 time zones from Los Angeles, California to Seoul, Korea. It's currently 10 p.m. in Korea and 6 in the morning in Los Angeles. So thanks for people for their dedication. So the objective of this course is to give you a little bit of, in some sense, concentrated introduction and overview of electrochemistry. The idea is to make you conversant so that you can use this as a point of departure to then go on in any particular field related to electrochemistry that you might want. The work that I'm presenting here, it's sort of the cumulative integration over 40 years that I have been at Cornell. I recently celebrated 40 years in July 5th. And so this is sort of a combination and integration of many years of teaching this subject. Also wanted to call out for the current people who are supporting our work. As you can see on the bottom on the left, Center for Synthetic Organic Electrochemistry. This is a center that Shelley Mintier leads out of University of Utah, and it's supported by the National Science Foundation. Muri and from the Air Force, centered at Emory University with Tim Lian. They've been also very supportive. And of course, Center for Alkaline-Based Energy Solutions, a DOE-supported Energy Frontier Research Center out of the Office of Basic Energy Sciences at DOE. And then on the top, sort of shameless promotion, Cornell University, group logo, and the so-called Abruna Energy Initiative. And so let's get started formally. So it says here, Fundamentals of Electrochemistry, a brief introduction to electrochemical phenomena and techniques. And so I really mean, fasten your seatbelts. This is going to be a very fast pace. And the idea behind providing you the notes is so that you don't need to take any notes, but rather your own notes. And so that's why, there's going to be about 3 or 4 installments. I think this first one is about 100 PowerPoint slides. I think overall, it'll be somewhere in the neighborhood of 300 to 400. And so, of course, we're taking off on flight. One brief comment, and it says copyright. I did this specifically because a number of years ago, I've been teaching this for a while, and I found out that, let's say, a professor at a distinguished university was using my notes to teach without even telling me. And so the purpose of the notes is for your benefit and your information. If you're going to make a course out of it, at least let me know and acknowledge that this is where the notes come from. So enough of preliminaries, so let's get started. The subjects that we will cover, you can see there's quite a few here. By general overview, you'll see in a second, so sort of framing electrochemistry within the larger context of chemistry at all. Very important aspects like potentials of electrochemical cells, and then much more deeper plunge into heterogeneous charge transfer kinetics, adsorption, theory of electron transfer. In that case, we will be talking about Marcus' theory of electron transfer, and using examples from inorganic chemistry as examples. It's a little bit easier to understand than the electrochemical double layer. So up to this point, it's going to be really more of the fundamental aspects of electrochemistry. And then subsequent to that, we'll start looking at various techniques. We will do reasonably thorough introduction and analysis of rotating this and rotating this electrode voltammetry. This is extremely valuable in many areas. Chrono amperometry, coulometry, and potentiometry for those who are interested in batteries and related areas. And then everybody's favorite cyclic voltammetry. And then depending on how much time we have left, we might go into applications and a few other specific subjects, including, for example, things like fuel cells or batteries or photoelectrochemistry, etc. So that's basically the intent in this case. And so here in a single slide is basically all we're going to be talking about. This is as basic or fundamental as an electrochemical process gets. And what do we mean by this? First thing you notice that we have this equilibrium. A is what you put in the beaker. Ox is what's going to be redox active at the electrode surface. So there can be some pre-equilibrium between A and Ox that will generate what ends up being the redox active component in the electrode reaction. And then you'll see the arrow, it goes from Ox to Ox adsorb. By that we mean that this species will feel the presence of the electrode potential, meaning there's an intimate interaction between the electrode and that species. That typically means that chemical species will be just a few angstroms or less than a nanometer from the electrode surface. As we'll see later on, the distances over which an electron can transfer is probably less than a nanometer or so at reasonable rates. From Ox, you go to red. The only difference is where the electron lies, because Frank Condon or the Bohr-Oppenheimer approximation, the nuclear coordinates are fixed in the time frame of an electron transfer. So you go from nuclear coordinates from Ox to red, the only difference being the electron. Once you do that, then the adsorbed form of the reduced species comes into solution and goes into products. And so this is as generic or general as an electrochemical reaction can take place. What we're going to do over the next 15 or so hours is fill in the gaps. How do we understand processes that precede or supersede the electron transfer, the kinetics of the electron transfer event itself, and the interaction of the electrode surface with those species? And so we can start with the definition. As it says here, electrochemistry is involved with the processes and factors that affect transport of charges, okay? Transport of charges. So to quote my good friend Deborah Rollison at Naval Research Lab, if charges move, it's electrochemistry. And so you have transport of charges across the interface formed between chemical phases. And so that in itself tells you that inherently electrochemistry is an interfacial discipline, meaning the interface is everything, period, end of argument. And so we will focus enormously on the interfacial aspects of electrochemistry and see where that takes us in terms of understanding. Now, there can be a variety of phases. In general, in electrochemistry, one of the safe phases that we're interested is an electrolyte. And so an electrolyte is a phase in which charges are transported by the movement of ions. And so you put a supporting electrolyte in solution, ions move in response to the electrode potential, as well as to any current that passes through that interface. The second phase could also be an electrolyte. It had to be immiscible with the first one so as to have a real interface. Or more commonly, it's an electrode, which is a phase, typically a solid, in which the transport charge is through electronic motion. And so we see the coupling of electronic motion or electronic movements with ionic movement. And so that interaction takes place at the interface. Remember that at all times we have to maintain electrical neutrality. So if we put an electron into the interface, we have to bring a counter ion to screen that charge. There will be no free charges floating around in this context. And so if we go a little bit deeper into different types of electrolytes, so an electrolyte typically is a salt that's dissolved and a big and dissociated. Why do you need it dissociated? Because if you have ion pairs, they will not contribute to ionic conductivity. And so the emphasis on dissolved and dissociated in a given solvent. And so here's some examples. Prototypical in aqueous media, potassium chloride in water. So here the ions, obviously potassium and chloride. You can have a wide variety of non-aqueous solvents. TBAP stands for tetrabutyl ammonium perchlorate, a very common non-aqueous electrolyte. Acetonitrile, a very common non-aqueous electrolyte. As we'll see later on, the advantages of using non-aqueous electrolytes is that it enables you a much broader range of applied potentials over which you can have electrochemical reactions. In water, you're limited by the potentials where hydrogen is evolved or oxygen is evolved, so-called hydrogen evolution or oxygen evolution. Thermodynamically, that's 1.23 volts. But I mean, because the kinetics can be sluggish and you can play some tricks, you might be able to expand that to a little bit less than 2 volts in that ballpark. For those of you who are interested in batteries, so lithium TFSI. TFSI is this species here, very common electrolyte in lithium-ion batteries. And dissolved PC stands for propylene carbonate, which is this character here. When we talk about batteries, we'll see that carbonates are very common, especially when you use transition metal oxides as cathode materials in battery applications. So these are salts dissolved in a solvent. You can also have molten salts. They come in a variety of ways. Aluminum chloride dissolved in butyl pyridinium chloride. This is a room temperature molten salt. They are, however, very sensitive to water and oxygen, so you have to be experimentally, you have to be very careful. Sodium polysulfides is a high temperature electrolyte used in sodium sulfur batteries, typical of things that were developed at General Electric. You can have ionic liquids, which are basically salts where there's no solvent, and so they're liquid at room temperature. Those have found a lot of use in battery applications as well as in synthesis. One of the issues, however, with ionic liquids is that they tend to be rather viscous, and so transport can be affected. We move on to solid electrolytes, meaning you're really talking about solid phases. So PEO stands for polyethylene oxide that has mobile protons from phosphoric acid. So-called beta double prime alumina, this is mobile sodium ions that move across that. Obviously, because these are solids, it requires relatively high temperatures. That is certainly the case on ITRA-stabilized zirconia, which is used in solid oxide fuel cells. You need to go to rather high temperatures, 700-800 degrees C, to overcome the barrier to transport. LiPON stands for lithium phosphoric nitride, which is a solid electrolyte used in lithium-ion batteries. You can have polymer electrolytes. The most common one, Nafion. Notice how I spell Nafion, because the name derives from sodium fluorinated ionomer. This is the key element in PEM, which stands for polymer electrolyte membrane fuel cells. You can think of Nafion as essentially sulfonated Teflon. So here you have what looks like Teflon, sulfonated side chains. This makes this environment very acidic. It forms inverse micelles, so you have channels where you have the ionized sulfonic acid groups that can transport protons. And so that's why you have, for proton exchange membrane fuel cells, this is the ionomer and membrane material that enables you to transport counterbalancing charges. More recently, a big push on phosphonium on alkaline fuel cells. This is a big part of the research in which we're involved. This is a phosphonium based polymer. This comes from my colleague Jeff Coates' laboratories here at Cornell. And the idea is that now you have a positively charged species appended to a polymer, so this can enable hydroxide ion transport, and so useful in alkaline fuel cells. In terms of electrodes, there's a variety of materials. Most common ones being metals. So you have things like platinum, gold, silver, and copper. What's common to all of these guys is that these are FCC metals. And so if you know the structure of one, you know the structure of all of them. We'll see later on that there's great value in doing electrochemistry where you can control the symmetry or the geometry of the surface. The most common ones, 111, 100, and 110, the low index phases, can have dramatically different activities. I include mercury here because mercury for the longest time was the electrode choice. It has some limitations and some advantages. The limitation is that it oxidizes rather readily at relatively low potential, around 0.2 volts or so. However, it has a very, very broad negative range. And so it's used in a lot of reductions, even in aqueous media at very negative potentials. In fact, you can reduce sodium ions to sodium metal in water at a mercury electrode and make a so-called mercury amalgam. Mercury was used because, let's say, 50, 60 years ago, it was very difficult to get clean metal surfaces. And mercury, because it's a liquid, if you have it in a so-called drop-in mercury electrode, every 3 or 5 seconds, you have a fresh electrode. So it makes the experiments much easier, but again, considering the limitations that it poses. You can have quasi-metals, things like carbon, boron, nitride, carbon in all sorts of different forms, be it graphite, be it glassy carbon, be it graphene, etc. Conducting metal oxides, these are typically non-stoichiometric oxides. The typical ones, ruthenium oxide and iridium oxide, that are used as oxygen evolution catalysts. Ruthenium oxide is part of so-called dimensionally stable anode that is used in the chloralkali industry. Tin oxide is also typically fluorine doped, or FTO, fluorine doped tin oxide is used also as a conducting oxide. It also makes reasonably transparent film, so you can make transparent electrodes, so you can do spectral electrochemistry in optical studies. Semiconductors, there's a very broad range of semiconductors. The prototypical one being silicon in all of its forms, and then a bit more sophisticated, gallium arsenide, the cat sulfide, TiO2, strontium titanate, tungsten disulfide, tungsten diselenide, etc. These are transition metals like chalcogenides. All of these things have been studied in great detail, and in particular, because of the relation to photoelectrochemical or solar energy conversion of energy, and also part of those, the perovskite that have been sort of the latest in those developments, with very high conversion efficiencies exceeding 20%, which is really astounding. One can also have electronically conducting polymers. The initial one developed at IBM, at the time called IBM San Jose, now Almaden, polypyrrole by Art Diaz. These are materials that upon oxidation typically will generate polymeric species that have metallic conductivity. So polypyrrole, polythiophene, polyaniline, sorry, I misspelled polyaniline here. PETA, which is a product of Bayer. It's an amazingly good polymer. It's very robust in use in many applications. More recently, 2D materials, graphene, molybdenum disulfide, molybdenum selenide, etc. What's typical or interesting of this material is that you can actually have a single layer of these materials. And so then it really begs the question, so what is electrochemistry like when your electrode is basically one lattice spacing in thickness, and the attendant changes in the work function, in the distribution of levels, etc. And so we come to one of the most important concepts of electrochemistry, which is the measurement of cell potentials. And what do I mean by that? So here you have your typical meter. So the numbers here is whatever numbers it might have. And so here you have metal 1 in blue and S for the solution. There's that interface. So you put that electrode in there. And you would like to be able to measure that potential. Unfortunately, you can't do that experiment because you need a second electrode. So you have M1S, you put the red electrode, so M2S. So you have the Democrats on the left and the Republicans on the right here. And so what this tells us is that rather than measuring a single electrode, in practice, what you do is measure the total potential difference. So here, emphasis on the total potential difference across a system of interfaces. In this case, the interfaces would be metal 1 to solution, solution to metal 2, and then across the terminals of the meter here. And so this brings up the issue. So how do we establish at least some way to rationalize potentials? And so in order to be able to compare different redox processes, we measure the values relative to a constant couple or redox couple, and this is what we call a reference electrode. And so in most electrochemical measurements, you will have a working electrode, which is the electrode at which the reaction that you're interested in takes place, and then a reference electrode that tells you where you are energetically relative to some known quantity. The more common reference electrodes, so here's the standard hydrogen electrode, 2 protons for 2 electrons going to hydrogen. This is arbitrarily defined as 0 volts and independent of temperature. There have been some estimates as to its absolute value. It's roughly 4.2 plus or minus 0.04 versus free electron in vacuum. That gives you some sense of correlating potentials in solution to potentials in vacuum, and that's a very powerful comparison to make. More practical ones, silver chloride, where you have silver chloride in equilibrium with silver and chloride ions. The potential of this 0.223 versus standard hydrogen. Calomel, which is mercurous chloride, less popular these days because it involves the use of mercury, 0.242 volts versus hydrogen. These are very commonly used, very easy to make, and very, very reliable in terms of the potentials. Now, one of the common confusions of electrochemistry is this idea of electropotential versus EMF, so-called electromotive force, which is, we can recast that question is, which direction is positive, or for that matter, negative? And the fundamental problem is that free energies are directional, meaning the sign means something. A delta G negative and a delta G positive mean very different things. A negative delta G means that you have a spontaneous process. A positive delta G is that you don't. And so we are then confronted with a difficulty because while free energies are directional, electropotentials are not. Okay, the electropotential is a value. Unfortunately, we all remember in freshman chemistry when we're balancing redox equations, it would tell you that whether the electron is on the left or on the right, you change the potential, and that was just a source of immeasurable anxiety on students and confusion. And so how do we keep things straight? And so we basically invent, as I say, and I mean invent, this is our creation, the concept of electromotive force. And electromotive force tries to integrate the fact that we can relate a free energy to NF delta E, meaning the electropotential, and we call this cell EMF or electromotive force. Now, the question is, how do we know if we have the sign correct? And the easiest way, and you can, please remember this one, if you write the redox reaction as a reduction, meaning electrons on the left, so ox plus electrons goes to red, then whatever that sign is the electropotential, okay? And then from there, you can figure out, if you're trying to figure out potentials of different reactions, then you can, add and subtract to your heart's content. This brings us to one of the key equations of electrochemistry, the Nernst equation. Formally, it tells us that the potential is related to the standard potential, which is potentials where activities are equal to 1. And then a factor RT, so the gas constant, the temperature, number of electrons, and Faraday is constant. And then the log ratio of the activities of oxygen red. Okay. And we say here, while Nernst equation strictly applies to activities, we almost never know what those values are. And so what do we do? Like every good scientist, we cheat. How do we cheat? Remember that an activity is a product of activity coefficient and concentration. And so if we assume the activity coefficients are 1, and as you say here, which we know is not true, okay? We still assume that. Why? Because it makes life easier. And so we assume that activity coefficients are 1, which you know is incorrect. And so it then enables us to use concentrations in place of activities when we know that really the Nernst equation applies strictly to activities. And so when we do that, then we get E equals 0, 0.059 over N, which is basically this Nernst factor at room temperature. This is where the famous 59 millivolts over N comes in, and the log ratio of the concentrations of oxygen red. We must also remember that here concentrations of oxygen red refers to surface concentrations, which again, we almost never know. And we'll figure out ways in which we can at least approximate them by doing the appropriate, let's say, conversions or experimental details. Here is a picture of Mikhail Warternens, who is responsible for this development. Now, we mentioned that electrochemistry is involved in the transfer of charge across interfaces. And so we need to sort of define clearly what we mean by oxidations and reductions. So in the top panel, we have a level here, an electron that's dictated by the Fermi energy of the material that you're operating. We're using the formalism of solid state physics, where potentials going up, negative, meaning it's more reducing, positive potentials going down, meaning more oxidizing. So let's assume we have a redox couple here in solution. And so we have the electron in the metal. We can adjust the potential and increase the level, the energy level of that electron until it's in coincidence with that level in solution. At that point, then the electron can go from the electrode to the solution. That's the electron transfer event. When the flow of charge or electrons is from the electrode to the solution, we call that a reduction reaction. So electron flow from the electrode to the solution. If, on the other hand, we start with the potential way up here, and we have a species in solution at this level, just the same way as we could increase the potential, we can lower the potential. And then when it's in coincidence with the level in solution, then the solution species can inject an electron into that level. So now we have electron flow from the solution to the electrode, and that's what we call an oxidation process. So let's have those really clearly identified, because it tells you the direction in which a net charge flow is taking place. As we mentioned before, I'll be drinking all throughout tea or water because this is very hard on my voice. We need to distinguish the idea of thermodynamics versus kinetics. Thermodynamics always rules, right? In the final analysis, it will have the last laugh because it basically tells us what is energetically feasible or not feasible. Kinetics tells us how fast a process might take place. And in this context, the electrode is not just a bystander. It can have an enormously important role. It is not just a source or sink for electrons. For example, let's consider the difference between platinum and mercury. And so if we have a platinum electrode, and let's say we start somewhere down here and start moving the potential up. So we start moving. When we get to this level, we can inject charge, turning iron 3 to iron 2. We keep moving the potential. We get to tin 4, 2 electrons in this case, to tin 2. We get to 0 volts, and we start evolving copious amounts of hydrogen. It's like you put Alka-Seltzer in water, you have enormous bubbling because you're generating hydrogen gas. You keep even more negative, you can reduce nickel to nickel metal. That would be on a platinum electrode. If we do the same thing, so this is on platinum, if we do the same thing on mercury, if we start here, what's going to happen? Actually, you can't do that one because mercury will dissolve. So this process is out at a mercury electrode. It's just too positive for mercury. So we're now here. And so we raise a level. And when it gets to this point, we can again carry out the tin 4 for 2 electrons to tin 2. We get to the hydrogen evolution, where in platinum, remember, there was this enormous evolution of gas. At a mercury surface, nothing, and I mean nothing happens. Why is that? It's that the kinetics of hydrogen evolution at mercury are horrendously slow. And so even though thermodynamically you should be evolving hydrogen, kinetically it's just too big a barrier to overcome. So then you keep going, and then you get to nickel 2, going to nickel 0. So now your mercury surface is coated with a nickel film. Nickel is better than mercury for hydrogen evolution, so you might start evolving a little bit of hydrogen evolution here because it's easier on nickel than it is on mercury. So clearly, the electrode has an enormous role to play here. It is not just simply a source or sink of electrons. There are other cases, however, where we're not interested in the electrochemistry of the electrode itself, but rather in solution species. So in those cases, we try to use electrodes that will be inert under the experimental conditions. Typically, those would be precious metals like platinum or gold, or things like glassy carbon, which are very common, especially for organic electrochemical transformations. And so a few definitions. Faradaic reactions, those are reactions where there is charge transfer, meaning charges are crossing the interface. In other words, something is being oxidized or reduced. If in the previous example, so over here, iron 3 getting reduced to iron 2, that's a Faradaic process. You can also have non-Faradaic reactions. And so these are reactions where there is no charge transfer, meaning nothing is getting oxidized or reduced. And so what does this entail? These are typically processes that involve double layer processes. As we'll discuss in detail later on, the moment you put an electrode in contact with a solution, there's a charge redistribution depending on the potential relative to solution. And so you're going to have, let's say in this case, you have a charge on the metal that has to be compensated by the charge in the solution. And so this gives that interface the properties of a capacitor. And so you can talk about the capacitance of that interface, which is the charge divided by the potential. You can also talk about the double layer current, which is the double layer capacitance, as we saw here, and then multiplied by dE dt, meaning how fast you're changing the potential. If you're doing cyclic voltammetry, this would basically be your sweep rate. And so that tells you that whenever you're sweeping the potential in an electrochemical system, there will be a current associated with a realignment or redistribution of charges. In this context, Q refers to charge measured in coulombs, E is the potential in volts, C is capacitance measured in farads. Remember, that's 96,487 coulombs per mole. That's a very big conversion factor, which helps you when you're trying to quantify things. What are the variables in electrochemistry? Potential and current are probably the most fundamental ones, and that we will go through great extent in describing how we measure them and the importance of that. If you're measuring the time evolution of that, so you have potentiometry, which is a measurement of the potential, amperometry, which is a measurement of the current. You can have charge, which is coulometry. Charge is a derived quantity because charge basically is the integral of current, with time, IDT. You can also have concentration in terms of an electrochemical variable. Temperature, unfortunately, is not that common, in some sense dictated by the fact that the temperature range for most liquid media is a bit narrow, but it's extremely valuable because it enables you to extract things like activation energies. And then, of course, time. And so when you combine time with the other measurements, you can have things like chrono potentiometry, chrono amperometry, chrono coulometry. That is, how does the potential change with time? How does the current change with time? How does the charge change with time? And so whatever measurements we'll do, during the course of this course will basically involve measurements either directly or time evolution of those as we try to understand electrochemical phenomena and electrochemical systems. The current potential curves, or IE curves, contain an enormous amount of information. They basically present how the rate of a reaction, which is the current. So immediately in your mind, current equals rate. So how the rate of an electrochemical reaction varies with the driving force. And so in any current potential profile, you have an enormous amount of information because it tells you what the rate is at any given potential. For those of you who are familiar with cyclic voltammetry, it might look something like this. So it tells you that at this potential, this is the rate. At this potential, that's the rate, etc. And we'll derive formalisms that will enable us to interpret potential energy changes, current potential profiles as a function of what the chemistry involved is. One of the fundamental concepts in electrochemistry is this one of overpotential. And we'll spend a little bit of time in here because there have been some confusion in the literature. And so overpotential is defined, says, the departure of the electrode or cell potential from its equilibrium value upon the passage of Faraday current is known as polarization. Okay, so let's start in the beginning here. So when you are at equilibrium, there is no net charge transfer. The system is at equilibrium. As we'll see later on, this is really a dynamic equilibrium, meaning that you have electrons, going from, left to right and also right to left in a dynamic process. And if you're at equilibrium, that means that there's no net current, no net charge transfer. The moment you deviate from that and you pass Faraday current, it involves a polarization, meaning you have to apply a voltage in order to give rise to the charge transfer. And so the extent of polarization, meaning how far you have to deviate from your equilibrium potential to pass current, is known as the overpotential. And so the definition, Greek letter eta, equals E minus E equilibrium. And so it's a deviation from the equilibrium value so as to pass Faraday current. If your process is inherently fast, then to reach a given current density, which is a rate, will require a small overpotential. If, on the other hand, you have a big barrier, there, in order to get any current, you need to apply a significantly large overpotential to be able to drive that reaction at whatever rate you desire. Without a doubt, the overpotential is present in all, and I mean all electrochemical processes. And as I mentioned here, it depends on the nature of the electrode, the current density, which is the rate, the nature of the electrode, like couple chemical reactions, anything and everything that's involved in an electrochemical process will be involved in the overpotential. There's some people who refer to being able to calculate, quote unquote, a thermodynamic overpotential, which to me is like, scratching, a blackboard with your nails. There is no such thing as a thermodynamic overpotential. What you can do is assume a model, whatever model you want. You can calculate the energies associated with levels in that model and calculate barriers within that model. And so you calculate the barriers based on your model. That is not a thermodynamic overpotential. That is a barrier calculated on the basis of a model. Overpotentials always refers to kinetics. Okay, let's keep that in mind. And so at a given rate of reaction, meaning a given current density, there will be an overpotential that can be, in some sense, apportioned to different contributions to the various steps. So MT stands for mass transfer overpotential, often called concentration polarization, meaning, as we'll see when we talk about transport, the concentration gradient will drive the kinetics based on fixed models of diffusion. And so if, let's say, you have an electrode surface, you're consuming material close to the electrode surface, because you're consuming it, the concentration will drop. That creates a gradient. That gradient is responsible for further mass transport. The higher the concentration you have, the higher currents you can sustain before you polarize, because you're basically at a rate that it's limited by how much stuff you can bring to the surface. You can have charge transfer overpotential or activation polarization. This means this is a regime where the electric reaction, the rate depends on the applied potential. When you're, and we'll see later on when we discuss this in detail, if you have a process, initially you'll be limited by the kinetics of electron transfer, so-called activation polarization. In that regime, the current will be potential dependent. At some point, you overcome all barriers, and instead of being then activation control, you're going to be mass transport control. So there's a transition from activation control to a mixed control to mass transport control. And we'll go in those in great detail. You can also have a quote unquote reaction polarization. For example, if your system involves a pre-equilibrium that generates the redox active species, or there's the subsequent electron transfer reaction, all of these things will contribute an effective overpotential to the reaction. And clearly, the overall or the total overpotential will be the sum of the individual contributions. So here we have mass transport overpotential, charge transfer overpotential, reaction overpotential, and however many other terms you want to include in your expression here. But the basic idea is that this will basically dictate what the overall overpotential is in your system. And so we're back to square one. You might recall that in the very first slide, we basically had Ox going to surface, a much more limited view of this expression. So we're now expanding this a little bit. And so now we can talk about bulk solution and the surface region. By bulk solution, we mean a region where the reactant doesn't know and doesn't care that there's an electrode somewhere, in this case to the left. There will be a region where the reactants will feel the presence of the electrode. It can be either within the double layer region where you have it's sensitive to the applied potential. It can also be the diffusion layer, which is the regime over which you can sustain concentration gradient. So you feel the presence of the field, not because you're feeling the field directly, but because of the consequences of changing the effective concentration close to the electrode surface. As we had before, we go from bulk to surface, meaning that that species feels the presence of the applied potential. From there, we go further and we call Ox prime here, meaning that the species now feels a very intimate interaction with the electrode surface, remembering again where are we? The Frank-Condon limitations that the species is not going to move, so nuclear coordinates are fixed in the time frame of electron transfer. So we go from Ox prime to red prime. The only difference is that now the electron has been transferred from the electrode to that species. That species can then dissolve from the surface and make it into the bulk solution. So now we're beginning to see the coupling of all of these processes that we mentioned before to the electron transfer itself. And so we can talk about mass transport, and we will talk about mass transport at great length further down in the course. And that involves how do you move from bulk to surface region. Electron transfer, which is very often one of the key components, that is, how does the electron transfer take place? By transferring, in this case, an electron from the electrode to the solution. It can be the other way around, where the species donates an electron to the electrode. Coupled chemical reactions. Here's a very, very old example, but it's very still very relevant. So the reduction of zinc in alkaline media, it exists as tetrahydroxyl zinc. In terms of the mechanism, it involves the loss of 2 moles of hydroxide. It generates zinc hydroxide, which is actually absorbed to the electrode surface. You reduce it, and this gives rise to elemental zinc. And this is of great relevance to, for example, zinc air batteries. You can have surface reactions, and we'll talk about adsorption at length. The thing to remember here is that an adsorbed species is a different chemical entity. It may have the same connectivities as the species in solution, but the fact that it's adsorbed tells you it's in a different energy state. And a different energy state is nothing other than a different chemical entity. So we need to keep that clear in our heads. So we mentioned mass transport in the previous slide. And so 3 modes of mass transport in electrochemistry that will be relevant to understand in some detail. And so the first one is diffusion. Diffusion is the movement under the influence of a gradient in chemical potential, meaning you have a concentration gradient. You will have partial C, partial X at X equals 0 at the electrode surface. We'll see that there's many techniques that are based on diffusional mass transport. And so we will talk about that at great length. Hydrodynamic or convection, this is when you either rotate the electrode or stir the solution to create a convective flux. And so the transport here is due to the movement or the displacements of volumes of solution to the electrode surface. And again, you can describe this in great mathematical rigor, as we'll see later on. Migration is a movement under the influence of an electric field. So for example, if your electrode is positively charged and you have a negative reactant, then that species will move towards the electrode surface just basically on the basis of that electrostatic potential. And so when we consider these three modes of mass transport, we can write basically the Nernst-Planck equation that gives you the flux. So J here is flux. Diffusion, DI, is a diffusion coefficient. Remember, it has units of centimeters squared per second. A typical vanilla flavor value for species in solution would be 9 times 10 to the minus 6 centimeters squared per second. You might wonder why I'm using that specific number. It's because very frequently you end up taking the square root of that. And at least for me, it's very easy to take the square root of 9 times 10 to the minus 6. Then you have the gradient here, partial C, partial X, meaning what is the concentration gradient as a function of distance, and typically at X equals 0, mainly at the electrode surface. So this is the contribution of mass transport due to diffusion. Migration, again, you have the diffusion coefficient, the concentration of the ionic species. Z is the charge, F is Faraday's constant, gas constant, and temperature. And then basically the electric field at the interface. Partial phi, partial X, what's the electric field gradient coming from the interface? And then convection, again, concentration, and it's basically the linear velocity. We will be considering one-dimensional flux to the electrode surface when we talk about rotating this electrode measurements. As we'll see later on, you can describe diffusion and convection with great mathematical rigor. The contribution from electrical migration is a lot more complicated. And so in order to accommodate for that, what we typically do in electrochemical experiments, we add a so-called supporting electrolyte that has two effects. One, it lowers the solution resistance. And secondly, it mitigates the effect of migration because it's typically present at a concentration of 100 to 1 to your redox active component. So for example, if you have a 1 millimolar solution of a species that is positively charged, but you have 100 millimolar of an inert electrolyte, the migration contribution to the current will be at most 1%. In most cases, that's negligible. Chemical reversibility. I mean, this goes back again to freshman chemistry. We're taught, that you can have A plus B in equilibrium to C plus D, and that this is a dynamic species. When you write something like that, implicit in this is that all of those species are chemically stable, at least in the time frame in which you're investigating that system. That's a bit different from electrochemical reversibility. And this is more of a thermodynamic concept. And so electrochemical reversibility means that one can shift the equilibrium with an infinitesimal change in the driving force. That is the potential. That is, with a delta V, we can change the direction of the electric reaction. Remember, at equilibrium, right, we have equal rates, back and forth, as you do in any system in chemical equilibrium, except that electrochemical reversibility refers to the fact that you can drive the reaction one direction or the other by an infinitesimal change in the driving force, which is clearly the potential. Put in different words, electrochemical reversibility means that the system is always at equilibrium with the electrode potential. And we'll see what some of the consequences of this statement are. And so the first statement is one of those truisms. It says, in principle, all electrochemical reactions are irreversible. Why is that? Because they take a finite amount of time to adjust to a perturbation. And what do we mean by that? Let's say we start with the system at equilibrium. So we have E equals 0.59 log ratio of red and ox. Remember that we're assuming activity coefficients are 1, and so we can have concentrations. If we change the potential, if we change this guy, let's say by 59 millivolts, that means that the ratio of ox and red has to change by a factor of 10, right? That's what I'm telling you. It takes a finite amount of time for that relaxation to take place. It is not instantaneous. And so therefore, in principle, all, and I mean all, electrochemical reactions are irreversible since it takes a finite amount of time for that relaxation to take place. However, that finite amount of time can be short and can be long. And so we then come up with a operational definition of what we call reversible or irreversible processes. And this is expressed in Ks, which is a heterogeneous charge transfer rate constant that has units of centimeters per second, or really linear velocity. And so here's some general demarcations, and these are clearly arbitrary, but they work in terms of giving you a sense for where you are in any particular case. If your system has a Ks of less than 10 to the minus 6 centimeters per second, we can consider this as being quote unquote irreversible. If it's above 0.1, we can consider that being reversible. If it's in between, and this gets very gray, so let's say somewhere in the neighborhood of 10 to the minus 3, 10 to the minus 4 centimeters per second, we call it quasi-reversible. Meaning it's going to matter a lot in terms of how you actually measure the rate. In fact, whether a system is reversible or irreversible or behaves reversibly or irreversibly really depends on your time resolution of your experiment. For example, if you can do, let's say, a charge injection experiment that takes, let's say, 10 nanoseconds, you're going to be sensitive to very, very fast processes. If, on the other hand, you're taking 5 seconds to measure the rate, even a very slow process will look fast on that time frame. So it depends on the inherent value of the heterogeneous charge transfer rate constant and the technique you use to measure that value. There is a maximum theoretical value for Ks of approximately 10 to the fourth, and this relates to the surface collision frequency, meaning, remembering, because you have a molecule that has to interact with the surface, that collision frequency, the rate of electron transfer cannot be any faster than that, because that's required for the process to take place. This is analogous to those of you who are more familiar with diffusion limited reactions in second order reactions in solution. That's of the order of 10 to the 11th per molar per second, as can be derived from the Smolakowski divide expression, meaning a diffusion limited reaction in homogeneous solution, we have an upper limit of the order of 10 to the 11th per molar per second. The equivalence for Ks in an electrochemical system is of the order of 10 to the fourth, which is blindingly fast. The fastest measured, let's say reliably measured values of Ks are on the order of, a few hundred to maybe 1,000. Going to 10,000 is extremely difficult experimentally. And so, let's go back. Okay. So we begin. Why is this not changing? Oh, dear. Second. This is not responding. I am having some technical difficulties here, folks. Hold it a second. Not good. Folks, I'm having some technical difficulties here moving. Let's try. There we go. Okay, folks, we are back live. Thanks to Michael Hint, who is the technology guru here. So we were saying we were here. We had talked about KS, and so we begin. What is this? Oh, come on. Oh, okay. It's just a little bit slow. Okay, so we begin our discussion of interfacial charge transfer kinetics. As we mentioned, in electrochemical phenomena, the reaction velocity or the rate is proportional to the current, right? If we look at the velocity, we can say current divided by NFA, number of electrons, Faraday constant, and area. If we look at dimensionally, it's moles per centimeter square per second. That has units of flux. And so basically what we're saying is when we look at a current density, we're talking about what is the flux of material being exchanged at that interface. What is different here is that the current will be potential dependent. And because of that, we need a framework that takes into account potential dependent rate constants. Okay. And so while in, let's say, homogeneous solution, we have temperature dependent rate constants, here we have the added variable, a potential dependent rate constant, because by the potential, we control with great finesse the driving force of the specific electrochemical processes. We can start with the most generic process. A, in equilibrium with B, we have K forward and K back. The forward velocity can be defined as the concentration of A times Kf. The reverse process is given by, but this is slow. There we go. The reverse is given by the concentration of B and the reverse rate constant. Obviously, at equilibrium, the forward and reverse velocity have to be equal and opposite, so there is no net conversion, and we talk about an equilibrium constant either in terms of the ratio of K forward and K back, or in terms of the concentration of A and B. It's basically freshman chemistry. Now, we're also taught, back, in freshman chemistry again, that at equilibrium, there is no net conversion, even though it's a dynamic process, meaning that at equilibrium, the rate at which A gets converted to B is equal and opposite to the rate at which B is converted back to A. And so dynamically, they're exchanging, but in reality, there is no net change in the concentrations. And so the velocity under these conditions is known as the exchange velocity, right? And it depends on the kinetic facility of that particular reaction, what barriers might be for the conversion of A into B and B into A. Now, in solution, many reactions have rate constants that vary with temperature as, natural log of K proportional to 1/T. That is, they follow the Arrhenius equation. So we write K equals A, typically quote unquote at pre-exponential because it comes before the exponent, and then some term that relates activation energy divided by RT to put it in the right units. And so we will see or find that a similar formalism, and I mentioned here, at least in the classical limit, meaning no tunneling, can be applied to electrochemical reactions. And so in this context, of activated process means that you have to overcome a barrier, which is inherent in this Arrhenius expression. We talk about the concept of a reaction coordinate. And what is a reaction coordinate? It describes the energy of a system as a function of one of its coordinates that can express progress from reactants to products. Meaning, if I go from A to B, I can choose one reaction coordinate that tells me whether I'm in A or in B. Case in point, this is hexaquo iron 3, hexaquo iron 2. The only difference is where the electron lies, right? However, the iron oxygen distance, and that's why I write this FeOH2, because the bonding is iron to oxygen in essentially octahedral geometry. That metal bond distance will be a function of the oxidation state of the metal. It'll be closer for iron 3 than it is to iron 2. And so as a reaction coordinate, if I say the distance from iron to oxygen going from large to small, that is a reaction coordinate because it tells me where the electron is. Is my species iron 3? Is my species iron 2? And that's what we can use this iron oxygen distance as a reaction coordinate for this process. And so this brings us to potential energy diagrams. So we typically have energy on the y and then a reaction coordinate on the x-axis. And we have parabolas that describe reactants and products. And so in this case, the blue is a reactant and the red is the product. And so a couple of things to keep in mind here. The difference between these two levels is the free energy of the reaction that's related to the electric potential. The difference between the bottom here and where those two things intersect, that will be the free energy of activation for the forward process, meaning reactants going to products. And conversely, the reverse one, from going from products to reactants, there's a free energy of activation for the reverse process. We can look at the reaction coordinates. So the reactant, this would be the equilibrium coordinates for the reactants and here for the product. And then there's the intersection region where those two parabolas meet. And those they have to meet in order for you to exchange from one set of coordinates to the other. And so if we look at a simple expression, so we can express the rate in terms of a transmission coefficient, as we'll see later on, it goes from 0 to 1. A frequency factor, the so-called KT over H, and then an activation energy term, which is the exponential of delta G star, the free energy of activation, divided by RT. It's worth noting that the enthalpy, basically free energy plus delta PV, but for condensed phases, delta PV is essentially 0 because these are incompressible phases, and so therefore we can make a reasonable assumption that the enthalpy is equal to the free energy here. Okay, so now we get a little bit more in detail, so let's go a little bit more slowly here. So we start with the general reaction. Ox plus N electrons goes to red. We have K forward, we have K backwards. No different than what we had before. We can express the forward rate in terms of a rate constant, Kf, the concentration of Ox, and this is equal to the current divided by NFA. So therefore, we can write that the cathodic or reductive current equals NFA Kf times concentration of Ox. Notice that these are surface concentrations, okay, which we said before, we almost never know what those are, but we'll get to that in a few minutes. Conversely, for the reverse reaction, so V backwards, or the rate for the reverse process, Kb, concentration of R. Again, we can write this in terms of the current. So in this case, the anodic, because it's oxidative, NFA. So we have the anodic current, NFA Kb, concentration of R. What's the net reaction? Basically, the difference between those two. And so we have that the net current is the difference between the cathodic and the anodic, equals NFA, which is constant, and then KFC0, KBCR. This is general. We have not made any assumption, any approximation. This is just straight, simple kinetics. Now, we start under standard conditions. And what do we mean by that? We assume unit activities, and we're at the standard potential. And clearly, we are at equilibrium. If we are at equilibrium, remember that the net current is essentially zero. If that's the case, that means that the cathodic equals the anodic equals this exchange current. So K forward equals KB equals KS, where KS is a heterogeneous charge transfer rate constant. Under these conditions of standard states, we can talk about the standard exchange current density. Typically, an exchange current density is illustrated by having a subscript 0. If it's standard, we put another 0 here, and that's why we have that over here. So NFAKS. From a potential NAD diagram perspective, we have what we have here in the yellow square here. So we have the system at equilibrium. Notice there's no driving force. The activation for the reverse of the forward and reverse process are the same. And so the activation energy for the anodic and the cathodic are one and the same, equals the standard free energy of activation. And so then we can expand and write that Ks equals a pre-exponential E delta G0 over RT. So this is what we had before, a little bit more explained. So we're looking at Ox going to red, assuming activity equals 1, and we're at the standard potential. Again, net current equals 0, meaning the anodic and the cathodic currents are equal and the same, except they have different signs. Under this condition, K forward equals K back, because you're at equilibrium, equals Ks, heterogeneous charge transfer rate constant, pre-exponential E activation energy over RT. And so then we can solve for the standard exchange current density as NFAKS. There is only one value for the standard exchange current density because it assumes that you are at the standard potential. That is different. You can have other exchange current densities, basically meaning that you're at equilibrium. So there's no net current, and that can be at different potentials. But the standard exchange current density is one value, and that's how we can talk about a value of Ks. So, I mean, if that was all there was to electrochemistry, we wouldn't be here, right? Because that was just boring as hell. We're just looking at paint dry on the wall because nothing is changing. So we can get a little bit more enthusiastic. So we can change the potential by an amount, let's say delta E, to favor the reduction reaction, meaning we're making the potential more negative. So what are the consequences of that? And this is shown in here. So when we apply a negative delta E, that will raise the parabola on the left by an amount NF delta E, where delta E is the value that we just put here. And so that makes that activation energy smaller. Conversely, the reverse process now has a higher activation energy. So now you see that there's a very big difference between the location of the minima in these parabolas, basically because we decided to change the potential. And so the change in the activation free energy for the forward or the cathodic or the reduction process is the standard one, which is what we started off with. And we're diminishing this by NF delta E that comes from the potential and a fraction of that alpha. Conversely, because we need to have conservation of energy, the anodic or the reverse free energy of activation starts again with the standard one. And now the difference, NF delta E, 1 minus alpha. And so that we have basically NF delta E as basically, in one case, it makes the profile higher for the reduction process. It makes the profile lower on the oxidative process. And so we have that now under these conditions, the free energy of activation for the reduction or cathodic process is decreased by a fraction alpha NF delta E. For the oxidation, it's increased by a factor 1 minus alpha NF delta E. And so alpha is known as a transfer coefficient, and it's a really important idea. It basically represents the fraction of the total energy change, NF delta E, that acts as to lower the cathodic energy barrier. And it's lowering by this alpha NF delta E. It reflects the symmetry at the intersection region, meaning those two parabolas, if they approach the intersection region with the same slopes, alpha equals 0.5. However, you can have differences in the slopes, right? And so alpha can be less than 0.5. It will typically fall in the range of 0.3 to 0.7. When in doubt, which is often, assume it's 0.5. Okay? You can have some asymmetries in those potential energy surfaces, but more often than not, between 0.3 and 0.7 are very reasonable values. If you see anybody claiming an alpha value of 0.1, you should get a little bit suspicious because that's very low. Meaning, in order to effect the same change in the rate, you need to have a much higher overpotential because only 10% of that is going in the direction that you want it to go. And so if we go back then to our previous image, so now we have that the reduction process, the cathodic reaction, has a smaller activation energy to get you to the intersection region. Conversely, the anodic process has a higher energy of activation, the difference being provided by this NF delta E. So this is where we are, right? And we're saying that Kf, A exponential delta G for the cathodic process over RT, we can expand on this because we know that this delta G can be given by this guy. So we have delta G0 plus alpha NF delta E over RT. We know that Ks equals A to the minus delta G 0 star over RT. And so therefore we can express Kf in terms of the difference in potentials. Notice, and this is something that I remember when I was a graduate student, that going from E0 minus E to E minus E0, you put this little negative sign in there. And then for the reverse process, basically the counter to that, K back, Ks E to the 1 minus alpha NF over RT E minus E0. So we can further develop this. So we now have an expression for the cathodic and the anodic current in terms of concentrations and rate constants. And so therefore, we can then again say the cathodic current, NFA, concentration of ox, E to the minus alpha NF E minus E0 for the anodic one, NFA, Ks, etc. So we can combine this. We know that the net current is the difference between the cathodic and the anodic. And so now we can bring in common factors here, and we have this reflects the reduction process, this reflects the oxidation process, which is a function of the concentration and how far you are from the standard potential. So we'll take limiting cases. So this expression right there we have made absolutely no approximations. Absolutely zero. So that's kind of a mouthful to try to absorb. So let's take some limiting cases. Let's assume I equals 0. If I equals 0, since we have I net is being divided by this number, that means that if this is 0, that means that Ks is large. Remember, NF and A are constant. If that's the case, what happens? If I net equals 0, that means that we can equate both sides, the cathodic and the anodic. We can take the ratio of ox and red. So we have C ox over C red, E1 minus alpha, E to the minus alpha, NF over RT, E minus E0. We can cancel the alpha, so we end up with C0 over CR, E to the NF RT, E minus E0. And this should start to look very, very suspicious, right? And in fact, if we take the natural log of both sides, natural log C0, NF RT, E minus E0, if we rearrange this, we get the Nernst equation, okay? Which is a kinetic derivation, what's fundamentally an equilibrium expression. And so let's make sure we understand this. We're saying that if we assume the process to be fast, Ks large, remember our definition of reversibility. The system is always at equilibrium with the electrode potential. And so that's what we're assuming. If that's the case, we have to get the Nernst equation back, because it's the one that relates the applied potential to the surface concentrations of ox and red, assuming that that process is infinitely fast, which we're assuming by saying that Ks is large or goes to infinity. And so that's, I still remember this, when I first saw this derivation, I thought this was really, really clever. And it's a way of understanding how you can get to the Nernst equation based on what is essentially a kinetic model. So having to operate, at standard potentials and very constrained environment is not really useful. And so we can, take a few more liberties here. And so we can take the cases where the surface concentrations of ox and red are not equal, or they're not equal to 1, but we are at an equilibrium potential. If we are at an equilibrium potential, remember that's our definition for net current being equal to 0. So we can talk about an exchange current, I0, but not, right, the standard exchange current density, because this is at a different potential. So if we go back, if we have one electron process and we have ox and red, if we change the ratio of ox and red by a factor of 10, and we change the potential by 59 millivolts, we can still be at equilibrium, but at a different potential. And so at that potential, the exchange current density will be different from the standard one. Nevertheless, we can express the exchange current density with I cathodic or I anodic, because they're going to be the same. NFAKS C0 e to the minus alpha, like we had before. And as I mentioned, this is the exchange current density, but not the standard exchange current density, because we are not at the standard potential. And so we have this expression that comes from here. There's more tedious algebra, and on this one, trust me, we end up with an expression down here. This is I equals I0, E minus alpha NF over T, E minus E equilibrium, minus 1 E minus I, 1 minus alpha NF RT, E minus E equilibrium. Remember that this is our definition of a potential. And so from here, we can come up to this expression, I equal I0, the exchange current, E to the minus alpha NF over RT eta, 1 minus alpha NF over RT eta. This is a well-known Butler-Fulmer expression. It is a fundamental equation of charge transfer kinetics. If you remember one equation from this course, that's the one. You should have it tattooed on your forehead so you don't forget it. Okay. Now, the Butler-Fulmer, as I mentioned, is the fundamental equation for interfacial surge transfer kinetics. And it tells us that the net current, the net current, is given by the net difference between the reduction and oxidation processes multiplied by the exchange current density. I0 clearly represents the current flowing at the equilibrium potential, meaning at zero over potential, meaning it's the inherent rate of the process when there's no driving force present. The other thing to notice is that the net current is exponentially dependent on the overpotential. It's e to the eta. And that will have enormous consequences when we try to figure out charge transfer kinetics in an experimental context. And so we can draw what the individual components are and the net current. So in the top panel here, this is where there's you can have the cathodic and the anodic. When the overpotential is zero, you can see that the net current, that the net current is zero as it has to be. If we go to more negative polarizations, the reductive or cathodic current increases, the oxidative or anodic current goes down. At very negative polarizations, the current is dominated by the reduction. At very positive polarizations, the current is dominated by the oxidative or anodic process. And that should come as no surprise. You also see that at zero over potential, this magnitude and this magnitude are equal and opposite, as they have to be, so that the net current is zero. Now, what are the variations in here as a function of, let's say, alpha and Ks? So remember, alpha gives you a sense of the symmetry. So here we have in the red alpha 0.5, and you can see that that profile is symmetric around eta. On the other hand, if alpha is bigger than 0.5, inherently, what are we saying? We're saying that a larger fraction of the free energy difference caused by the change in potential is driving the reduction reaction. And so you'll see that for the same overpotential, let's say, for the same overpotential, the current here is much higher than the current here. And that's because a larger fraction is going for the reduction. On the other hand, if alpha is less than 0.5, that means you're favoring the oxidation reaction. And so you have the complete opposite. And so in the oxidation reaction at a given overpotential, right, then this current is clearly higher than this current at 0.5. And so it gives you a sense for how much the value of alpha affects your current potential profiles, because it tells you what fraction of the free energy change associated with the change in potential goes towards either the reduction or oxidation reaction. Remember, alpha and 1 plus and 1 minus alpha has to be equal to 1 for energy conservation. And then finally, we look at the value of Ks in this profile. So we're looking here at anodic and cathodic currents. So here, Ks for A is bigger than B is bigger than C. So how does that reflect it in here? If we look at the potential energy profiles, right? And we're saying, I want a given rate. Let's say I want this rate of this current density. I go across. To achieve the same rate, which we're controlling by the current density, in the case of A, I apply this much over potential. In the case of B, this much over potential. And in the case of C, this much over potential. And so clearly, to achieve the same rate, I have to expend a much higher over potential and in C than in B than in A, because Ks is A bigger than B bigger than C. And the same holds here in the oxidative processes. A bit more on Butler-Fulmer. And so if we look at current density as a function of applied potential. In the interval where the current is potential dependent, as you can see here, this so-called kinetically limited regime, you can see that the current is dependent on the applied potential. Eventually, it will reach a mass transport limit. So it's no longer kinetically controlled, meaning you have applied a large enough overpotential to overcome any and every kinetic barrier. If you have another process that is more sluggish, then in order to achieve the same current density, you have to apply a much higher overpotential. And so again, this tells you that the blue, K for this guy is bigger than for the magenta line here. The point here is that you have a regime where you're kinetically controlled, followed by a regime where you're mass transport controlled. And so just to take a step back and look at where we are, we started with a very simple process. Ox plus n electrons goes to red, we have K forward and K back. We could define a cathodic and an anodic current, assuming an activation process, basically Arrhenius like kinetics. We could talk about the net current in terms of the exchange current density, NFA-Ks, the difference between the reductive and oxidative processes. When we assume large Ks, we basically obtain the Nernst equation. Under conditions where we are at equilibrium but not understand the conditions, we could basically get the Butler-Fulmer expression. Okay. Now, again, we're trying to figure out how to make use of all of these expressions. So we consider limiting cases of the Butler-Fulmer equation. And we start with small overpotentials, okay? And so from a mathematical standpoint, if the argument in an exponent is small, then we can linearize that. E to the x is equal essentially 1 plus x for eta small. If we do that, then the Butler-Fulmer becomes I equals I0, alpha NF RT eta minus 1 minus NF RT eta plus alpha NF eta over RT eta. What cancels here? The ones cancel and the alpha NF cancel. So you're left with I equals I0 NF eta over RT. Meaning that for small overpotentials, the current voltage relationship will be linear. And so we have linearized the Butler-Fulmer expression. The current will be a linear function of the overpotential. We can take this a little bit further and using just, Ohm's law, E equals IR, we can talk about the so-called charge transfer resistance. And so we have NFI0 that comes from the expression that we saw above. And so the charge transfer resistance, RT over NFI, if you do dimensionally, this is voltage and this is current, so E equals IR. And so the charge transfer is sort of a crude measure of the kinetic facility of your process. And just for the sake of argument, a charge transfer resistance of 25 ohms corresponds to a current density of 1 milliamp per square centimeter. Depending on the application, this can be either large or small. If you're working on, let's say, fuel cells, that's an intolerably large overpotential since you're trying to drive, amps of current. If you have 25 ohms, then you basically are dropping volts of potential in your cell. On the other hand, if you're looking at kinetics of charge transfer in a homogeneous system with dissolved intermediates, that's much more tolerable. And so it depends on the experiment that you're doing and the current densities that you're applying. So that was a small overpotential. Obviously, if we go small, we can go big. So what are the consequences? Remember that in the Butler-Fulmer, we have two components, the cathodic or reductive, the anodic or oxidative. If we make one of those terms, if we make eta large, remember eta has a sign, eta is either positive or negative. If we do that, then one of those two terms is going to drop off because we're having, an e to a big negative number versus e to a big positive number. So one of those terms will drop because it will become insignificant relative to the other. That's the case, and we can ignore the reverse reaction. Okay. And so if we assume a negative overpotential, that means we favor the reduction, then we get that I equals I0 e to the minus alpha NF eta over RT. If we take the log of both sides, ln of I0 minus alpha NF eta over RT, or we can rearrange this at eta equals 2.3 RT over NF log I0 minus 2.3 RT log I. This is usually expressed as eta equals A plus B log I, which is known as the Tafel equation. And so the Tafel equation derives from the Butler-Fulmer at large overpotentials. And that's because we have a large enough overpotential that we can ignore the reverse reaction. And so if we look a little bit further into the Tafel equation, we can see, so here you have, eta equals A plus B log I. A basically has this value, I0, and B has this value. At 25 degrees C, B equals 0.059 over alpha N, which is come as no surprise. And so for N equals 1 and I equals 0.5, basically vanilla flavored conditions, beta, the slope will be 118 millivolts, which considers a quote unquote typical Tafel slope. Basically, it comes from having 59 divided by 0.5 and 1 electron. You divide by 0.5, you essentially multiply by 2. So 59 times 2 is 118 millivolts change. And what that means is under these conditions, in order to increase the current by a factor of 10, you need to apply an overpotential of 118 millivolts. The larger the value of the Tafel slope, the more sluggish your reaction is. And people will make, big arguments based on the Tafel slope, which can be useful, but it can also be a little misleading and confusing. Now, if we look at a plot, so here we're plotting log I versus eta. So here, 0 overpotential, so basically 0 current. And the blue is a plot assuming a Tafel expression. In order to comply with large overpotential, you have to be probably at least 100 millivolts beyond the equilibrium potential. And so you can notice that around 100 millivolts here, now this becomes linear. And so what you can do, extrapolate back to eta equals 0, and that intercept will tell you what the log of the exchange current density is. And that's one very nice way of guesstimating what your exchange current density is from the intercept of the linearized part of the Tafel slope. Beware, because some people will try to do that by using conditions that do not apply. A 20 millivolt overpotential does not ensure that you're in the Tafel regime. Okay. There's a question, are we assuming that this is the equilibrium for each overpotential, or that the current will bring the system? So, okay. Whenever you displace a potential, right, you put the system away from equilibrium. So the system will readjust by having the surface concentrations achieve that. In order to do that, you need to pass the current to achieve that. So that's where that comes from. That was a very fast introduction to charge transfer kinetics. The next subject here is adsorption, which is of enormous fundamental importance here for this course. Let's take a step back and think what we mean by adsorption. As with any chemical reaction, why do chemical reactions take place? In essence, to lower their energy, right? That's why negative delta G is favored because the system goes to lower energy state. If something adsorbs, it's because the adsorbed state is more stable than the non-adsorbed state. If it's in a different energy state, I don't think it's so much of a stretch to say that's a different chemical entity. It may have the same connectivities, the same, atom connections, but it is a distinct species because it's at a different energy state. If I just gave you generically, I have two energy states occupied by molecules A and B, you would inherently assume that they're different, as you well should. In this case, the trick is that it's still the same, say, molecular structure, but the fact that it's adsorbed tells you that it's in a different energy state, and therefore the reactivity will be very different. And so we need to understand such phenomena because it's intimately related to electrochemical processes. And so we have here an equilibrium of oxygen solution and oxidorb. So you can define potentials that apply to the adsorbed species, to the solution species, or the adsorbed species. And this, as I mentioned, really different reactants. They have different E zeros. And so we must treat them as different reactants. And so in order to do this and to develop a formalism that will enable us to do that, we need to understand the concepts associated with adsorption in terms of trends, thermodynamics, and kinetics. In the simplest of cases, we can think of adsorption equilibrium as shown in this profile here. So we have the green here is the electrode surface, S stands for solvent, and so what we have is an electrode coated with a layer of solvent. We have a species in solution that's solvated, and so if that species adsorbs, it then becomes in intimate contact with the electrode. There's sort of an inherent interaction in there. In so doing, it liberates n moles of solvent. It displaces some solvent from the surface. If we assume that the solvation here is 4 molecules, in the process of adsorbing, this n would be 5, because you have 4 from these guys and 1 from the surface. And so what does that tell us? That the adsorption will have contributions, one that is enthalpic and another one that is entropic. The enthalpic refers to the interaction of the molecule with the surface. The entropic refers to the fact that if you're liberating 5 water molecules, you have a positive entropy change that helps you in the overall free energy difference. And so what are the driving forces for things to adsorb? So the driving force can be provided by a variety of phenomena. Hydrophobicity of the adsorbate. If you're in aqueous media and you have a hydrophobic molecule, then that species will feel much more comfortable adsorbed to an electrode surface because the repulsive interactions are going to be mitigated because towards the electrode side there's no solvent. And so we'll see how hydrophobicity, hydrophilicity can have enormous effects on whether a molecule adsorbs or doesn't adsorb and the reactivity of that molecule. We can have electrostatic attraction, meaning depending on the potential of the surface, if the electrode surface has a net positive charge, it will attract negatively charged species, and conversely, it will repel positively charged species. So this process is known as physisorption, meaning it responds only to the electrostatic field at the interface relative to the charge on your reactant. You can go beyond that and have some level of adsorbate electrode bonding, meaning chemisorption. So a chemisorptive bond implies something above and beyond simple physisorption or electrostatic interactions. Case in point, quinones, which are one of the best known, oldest, and most heavily studied redox active molecules. So the redox transformation, you go from the quinone on the left, it's a 2-proton, 2-electron system to give you the catechol or the hydroquinone on the right. So you exchange 2 electrons and 2 protons, proton-coupled electron transfer. Quinones can adsorb onto platinum electrodes, and the adsorbed monolayer is not redox active. Let me repeat that. Quinones can adsorb to platinum, they are not redox active. And so clearly, the electrode is having an enormous influence on this process. However, if prior to that, you take that platinum electrode and immerse it in, let's say, 1 millimolar solution of potassium iodide, that generates an adsorbed monolayer of iodine on the surface. And if you then adsorb the quinone, it is fully redox active. So if you've gone from something that is not redox active to something that is redox active by controlling the composition of the interface. So please don't tell me that the interface doesn't matter. Surface composition is absolutely critical. And as you can see in this example, it can be the difference between something being active and non-active in an electrochemical context. There was this accounts of chemical research by Fred Anson, formerly at Caltech. He's been emeritus now for a number of years. This is an oldie but goodie. Fred Anson was one of the pillars of electrochemistry in this country for many, many, many years at Caltech. He was probably also the tallest electrochemist. He was like 6'8" or 6'9", and in any conference, you could tell where Fred was. He was also fond of martinis, so at many Gordon conferences, he would have like a gallon of pre-mixed martinis, and sort of he would enjoy himself. So he came up with this nomenclature, dividing adsorbers in terms of class. I would recommend reading this article. You know, it's almost half a century old, but the concepts are still crystallinely clear and equally applicable today. And so he starts with defining classes of adsorbers. So class 1A, it says simple inorganic ions that interact through electrostatic interactions, meaning physisorption with the surface. Perchlorate, nitrate, phosphate, PF6, BF4, fluoride, cesium, tetraalkyl ammoniums. Some of these can be a little hydrophobic. So for example, tetraalkyl ammoniums, and they can disrupt the water structure because of the hydrophobicity of that environment. But the assumption here is that these ions interact only through electrostatic interactions, meaning they respond to the net charge on the electrode surface. Class 1B says much stronger interaction than 1A. And these are ions that go well beyond simple electrostatic interactions. That is, there'll be some bonding between the adsorbate and the electrode. So there's a net bond between that adsorbate and the electrode surface. Class 1B ions tend to be large anionic and polarizable. Why should that be? Because that's where the electrons are, right? If you're a big fat iodide anion, you have a lot of charge density you can slosh around. If you're a fluoride anion, there's no chance in hell that that charge is going to be shared. Okay? Now, because of the strong interaction, class 1B anions are said to be specifically adsorbed, meaning there is a net interaction, a bonding interaction with the electrode surface, especially when the surface is positively charged. Especially when the surface is positively charged. We will see when we talk about double layer structure that specific adsorption of anions can actually change the potential on an electrode surface. So you might think that you're applying a positive potential when in fact the electrode is negatively charged because you have an overcompensation due to specific adsorption. And unless you know that, you have no idea what the potential is at your interface, And conversely, you have no idea what the driving force is for your reaction. Not surprisingly, specifically adsorbed ions are typically things that are large and polarizable, things like chloride, bromide, iodide, isocyanate, cyanate, sulfides, etc. What's common to all of these things is that they're anions with large charge densities. In general, cations do not tend to specifically adsorb. Why? Because there's no electrons to share. And so it should come as no surprise that the realm of specific adsorption is the realm of anionically charged species, especially at positive potentials or net positive charge at the electrode surface. Class 2, these are neutral organic molecules that adsorb because of hydrophobic interactions. In general, the less soluble in water, the more strongly they tend to adsorb. And that's because if you think of solubility as a measure of how well a molecule interacts with its solvent, the less soluble it means that it really does not want to go in there. Certain things that help adsorption, pi electrons and lone pairs, right, tend to enhance adsorption. So what are we talking about? We're talking about aromatic molecules with heteroatoms. Why? Because that's where the electrons are. If one looks then at what would be the profiles of species as a function of applied potential and the, let's say, coverage on the surface. So we start with the simple ones. Remember 1A, that these are species that only interact with the electrostatic field that they interface. So here we're plotting the amount of stuff or the amount of adsorption versus the charge on the electrode surface. So you can start with a neutral surface, positively charged, negatively charged. If we look at the class 1A ions, so here we look at the cations. So on the surface has a net negative charge, we see that the concentration of the species goes up. On the other hand, for 1A anions, as you go, if you charge the electrode surface positive, then basically it comes up. Notice that when you're at zero net charge, there is no adsorption, or what in the lingo of adsorption would be called surface excess of either cations or anions at that interface. We now compare with 1B anions. Remember, these are species that can be specifically adsorbed. So if we look at the species, we notice the dashed purple line, and we notice that at positive, charge densities, the amount of stuff is much higher than simple electrostatics. This much difference. Moreover, even when the net charge on the surface is zero, you still have adsorbed stuff. It takes a much more negative charge to completely displace that species. And we can take that difference as a measure of the strength of the interaction. The more strongly absorbed an anion is, the more of a negative charge on the surface you'll need to displace that charge. And then finally, the neutrals, there'll be almost like so at zero surface charge, you have a maximum because that's when the electrostatic repulsions are minimized. If you go either positive or negative of that, then you see, typical profile like this going into zero. So at significantly positive or negative surface charges, organics really don't want to be there. However, when it's neutral, then you have a high propensity for these species to adsorb. It's interesting and revealing to consider surface coverage. What's the equivalent volume concentration of a surface at monolayer coverage? Let's assume a surface is 1/10 to the 15th atom per square centimeter. That's typical of a metal surface, okay? And assume that you have one adsorbate per surface atom. So you have 1 times 10 to the 15th atom per square centimeter, divided by Avogadro's number, and you have 1.67 nanomoles per centimeter square. If you assume a thickness of 3 angstroms, which is a typical atom size, then you will come up with a concentration that is 56 molar. Let me repeat that. A one monolayer of one adsorbate, where you have 1 atom per surface atom site, have an equivalent volume concentration of 56 molar. Pure water is 55 molar. And so when you think of what are the consequences of having a monolayer of an adsorbate, it's enormous. It's difficult to conceive of that because we're used to thinking, well, how much could a monolayer be? After all, it's only 1 atom or molecule thick. Sure, but the volumetric equivalent is enormously large. And so, for example, even at low surface coverages, if I told you, do you think a 10% monolayer is concentrated or not? I'm pretty sure that a high percentage of the current 230 participants now would say, probably not so strong. And you would be incorrect. 10% of a monolayer is of the order of almost 2 molar. And I don't think anybody thinks that 2 molar is a dilute concentration. Why do I mention this? Because if you have adsorbed intermediates in any mechanistic pathway, then the contribution to the overall rate is going to be very significant. It says, where would non-charged inorganic molecules like water fit in? I mean, if it's uncharged, then they don't respond to the field. And if the charge density is low, then basically very little, if any, interaction as a function of the applied potential. However, you can have species that are attracted because of dipolar interactions. And so water can be oriented, the dipole of water, and we'll talk about that when we talk about double layer, as a function of the potential. If there's zero net charge, then there's really no driving force for that. A little bit more on numbers. For a surface, as we mentioned, 10 to the 15th atom, which is typical of a metal, a 1 electron redox process corresponds to an equivalent capacitance of 1.6 and 10 to the 3rd millifarads per meter squared. And what the hell does that mean? Basically, this is about 100 times the typical double layer capacitance of your electrode. What does that mean? That means if you're doing studies where you're looking at the double layer of your interface, you have to be really, really, really careful if you have any process that involves charge transfer, because it can overwhelm the capacitance that you measure. For adsorbed species, the contributions, it just from double layer charge are small, but ferritic processes, as you saw, are enormously important. So one has to be very, very careful when interpreting the double layer capacitance. So it's a question: is it reasonable to assume 1 adsorbate molecule per atom on the surface? Organic molecules can be big, absolutely so. But for example, if you take something like carbon monoxide on a platinum surface, it's 1 CO per surface platinum atom. Obviously, if you have a larger molecule, then it will be a lower surface coverage. I mentioned the specific case of 1 because CO is a very strong adsorbate, and it's one of the most common adsorbates, one of the most highly studied adsorbates, especially in platinum. I'm guessing there's probably at least, and I'm not being whimsical here, probably at least 2,000 publications of CO on platinum in different forms. Now, we've been talking about adsorption of species. How do we develop a framework to understand how, the surface concentration of species changes with driving force. And this is where the concept of adsorption isotherm comes in. And so an adsorption isotherm, I said, Sears describes the relationship between the activity, notice activity, of a species in solution and the amount of material adsorbed per unit of area or surface coverage, usually given the letter gamma from the Greek letter gamma. So the question is, how does the surface coverage, gamma, change as a function of the solution activity of a species? How do we set up this equilibrium? Basically, we set up the condition where the electrochemical potential, I guess we didn't discuss electrochemical potential. Electrochemical potentials is a chemical potential where you also include the electrostatic field, okay? And so the condition of equilibrium is that the electrostatic potential for the adsorbed species has to be equal to that in the solution species, because that defines an equilibrium condition. When you achieve that, then you have an equilibrium relationship between the solution activity and the surface coverage. But the condition is that the electrochemical potential for both the adsorbed and the solution species has to be equal and the same. If not, there will be a net transfer to achieve equilibrium. And so if we look at how do we get a little bit more quantitative, so here we have the electrochemical potential for the adsorbed species, the electrochemical potential of the solution species, RT ln of the activity, RT ln of the activity. This, as we mentioned, are the standard electropotentials. And when we equate those, we can then look at what the free energy of adsorption is by comparing the differences in the electrochemical potentials. So we can define the free energy of adsorption in terms of the two components. For the adsorbed species, the species in solution. We can then go back and say the activity of the adsorbed species is the activity in solution multiplied by this beta factor, which takes into account the free energy of adsorption relative to the thermal pool. And so we can write that the activity of the adsorbed species equals the activity in solution times this beta factor. And this is the general form of an isotherm. And notice we have made absolutely no assumptions in here. And we're using activities. I mean, we could in principle say that this is a concentration, but the thermodynamically relevant parameter is activity, not concentration. So that the question is, can we come up with expressions that are a bit more user-friendly than this one? This will become surface coverage. This will become solution concentration. This basically reflects how strongly a species is adsorbed. And so different isotherms differ in the functional form of the activity in solution and surface coverage. The most common and the most widely used is the lime-muir isotherm. Why? Because it's easy. So what are the assumptions in the lime-muir isotherm? It assumes no interactions between species. Translation, the free energy of adsorption is not a function of coverage. So for example, if I have a species let's say with 9 sites, if I occupy this site with an adsorbate, it means that this one, this one, this one, and this one, their free energies of adsorption are not affected by the presence of this guy. And we almost intuitively know that that can't be the case, but we assume that it is, okay? That is, the free energy of adsorption is not a function of surface coverage. We'll see later on isotherms that take into account such interactions. The other one is no heterogeneity of a surface. That is, all surface sites are equal. And again, that can't be right. If you start, if you have, a 1-1-1 surface, that's hexagonal, right? Versus a 1-0-0 or a 1-1-0, those are very different geometries, right? So here you have 1, 2, 3, 4, 5, 6. If this is a central one, this, in close contact is a bit more expanded. And so even though we assume that all surface sites are equal, in reality, especially on well-defined single crystal surfaces, they're not. And then we also assume that there is a maximum coverage that typically corresponds to a monolayer, and that's a saturation coverage. And from that, then we can write that gamma I, meaning surface coverage at some solution concentration I, is given by the saturation minus that one, the parameter that takes into account the free energy of adsorption, and activity in solution or concentration. It's often convenient to define a fractional coverage so that you can compare different species. If you have an absolute surface coverage, that makes life a little bit more complicated. And so you can talk about the fractional surface coverage theta. And so gamma I over gamma saturation goes from 0 to 1. When you have very little, then the fractional coverage is 0. When gamma equals gamma saturation, we basically go theta equals to 1. If you do that, then you can have basically expanding on the similar expression, theta 1 minus theta equals the same term as you had before. Now, as we mentioned, the most commonly used isotherm is the Langmuir isotherm. Recall that the isotherm was given by this expression. It's a relatively simple derivation that we'll do here. You can also do it by statistical mechanics. It's a little bit more involved, and you get to the same answer. So we'll do it the easy way here. So you consider a surface with a given number of adsorption sites. And theta represents the fractional surface coverage. That means how many sites are occupied, and obviously then 1 minus theta corresponds to the number of available sites. We assume a system that is at adsorption equilibrium, meaning the species in solution is in equilibrium with the species adsorbed. So we can write the rate of adsorption and the rate of desorption, and then we can equate those two. So what are those? For the rate of adsorption, we have the concentration of M in solution. We have the rate of adsorption, K adsorbed, and the number of available sites, 1 minus theta, right? Meaning, what's my concentration in solution, how fast it can do it, and how many sites I have that I can get into. For the desorption process, we have surface coverage, how many sites, what fraction is covered, and what's the desorption rate constant. And so at equilibrium, these two processes have to equal and opposite. So you can equate this guy and that guy. So we have Cm K adsorb 1 minus theta, as we had here, equals K desorption theta. We can then very simply clear and express in terms of theta. So we move 1 minus theta to this side and K desorption here. So we have that theta 1 minus theta, K concentration, K adsorb, K desorb, and basically this is the equilibrium expression. So we obtain the Langmuir isotherm as we saw previously. It's a very simple derivation, but it's useful to for us to get a sense for how this comes. Notice that this assumes a reversible process. Very often adsorption might be irreversible, and so one has to make some sort of extra thermodynamic arguments to at least get some sense for how these things work. Now, as we mentioned, the Langmuir isotherm assumes no interactions. And then there's certain isotherms that can take into account, and this is typically done by introducing an interaction parameter, typically G. There are two isotherms that are typically used. Temkin isotherm, Oh, come on. Oh, no. Sorry, folks, I screwed this up again. Oh, okay. Are we? No. Oh, crap. Can people still see the presentation? If anybody can answer that in the question and answer. Okay, thank you. Okay, so let's continue. So in the Temkin isotherm, we have G in this term. In the Fromkin isotherm, we have it on the exponent. And so one can have gamma I related to the G term here, or whoops, in the Fromkin isotherm term. Oh, okay, so we cannot see this. Wow. No, we can't see. Okay, so give me a second. Oh, crap. Oh. Michael, if you're hearing me, I need some help. I don't know what I did here. I did something here. I don't know what. Oh. So I was sharing, and then I don't know what I did. And let me. No. Already. So let's see. So since 25 of you said that you couldn't hear me, you see it. Can you see it now? Please say yes. Another 25. And the answer is yes. Okay, very good. And so, so basically, it depends on where we have the interaction parameter here in the pre-exponential term or in the exponential term in the Fromkin. So we can expand the Fromkin isotherm to have basically two terms in here. And why is that important? Because depending on the magnitude of G, the interaction parameter, we can have sort of limiting cases that are really very helpful. Now, what do we mean by an interaction parameter? A positive value implies an attractive interaction, meaning a positive value of the interaction parameter means that as you absorb stuff, it gets easier to absorb more stuff. And we'll have, what the consequences of that are. A negative value implies a repulsive interaction, meaning as you absorb more stuff, it gets increasingly more difficult to absorb more stuff. Now, when G goes to 0, very conveniently, Fromkin becomes linear. And you can see this here, because when G goes to 0, right, you basically have e to the 0 is 1, so you have beta a solution, gamma I, gamma S, and this is basically the linear isotherm. And then also when, for Fromkin and Tenkin, when at half coverage, Fromkin becomes Tenkin. So what do these things look like when you plot them? And so here we have a linear isotherm, and we compare it to the Tenkin isotherm. If you look at the Tenkin, this is a lot sharper than this guy. Okay. For those of you who are biochemists, it's basically like a Michaelis-Menten type, profile. Now we can look at the absorption isotherm for linear and compare to attractive or repulsive interaction. So here the linear is this line. An attractive one means that for a given driving force, I have a higher coverage. For a repulsive one, it means that I have a lower coverage. One way that it's useful is to start assembling an isotherm at relatively low driving forces or low concentrations, because very close to the origin, they basically converge, and then you can sort of get a sense in which direction they're going to go. Let me take, I need to get a little bit more water. I'll be back in 2 minutes, okay? It's just my throat is killing me. Hello. No, I'm okay. I just need to get a drink of water because my throat was just killing me. Thank you. Yeah, bye. Okay, so we're back. looking now at adsorption kinetics. And so when you think about the kinetics of adsorption, as in many processes, you can either be kinetically controlled or diffusion control, meaning in kinetic control, there is a barrier that has to be overcome. In diffusion control, basically have strong adsorption and fast kinetics. And so in this context, for kinetic control, you can look at the coverage as a function of time. So gamma sub t is gamma equilibrium, meaning what the equilibrium coverage is under the experimental conditions, and then 1 minus e to the k concentration t. And so this is exponentially dependent on time. Gamma t, gamma e. So when you're kinetically controlled, the increase in surface coverage will be exponentially dependent on the time, concentration, and the kinetics. On the other hand, if you're looking at diffusion control, this is typically the case of strong adsorption, fast kinetics, quote unquote, semi-infinite linear diffusion. This comes from fixed loss of diffusion that we will talk about when we start talking about transport. But the expression is that you have gamma at some time t versus gamma of the equilibrium or saturation equals k is a constant, which is this geometric factor, concentration, gamma saturation, and then square root of dt, where d is the diffusion coefficient. And so what this tells us is that with simple plots, we can tell whether a process is kinetically controlled or diffusion controlled. If one can do two experiments and basically figure out whether the process is kinetically controlled or diffusion controlled. And what would that be? So let's say I have a surface, I have some solution species. One way to change mass transport is to stir the solution. So if I look at a system, look at the adsorption kinetics, I measure the coverage as a function of time, and then I stir the solution. If it changes, that means I'm diffusion control. If it doesn't change, I'm kinetically controlled. And then you can do the appropriate analysis. But that's a very simple way of telling which one is controlling, whether it's kinetic or diffusion control. Notice also, as I mentioned earlier, when we were talking about diffusion coefficients, I mentioned that very often you end up taking the square root of the diffusion coefficient. So now the value of 9 times 10 to the minus 6 centimeters squared per second makes a little bit more sense. Let's start a little bit. I mean, we're 11:35. Let's just start a little bit on the Marcus theory, and we might go over this again tomorrow. But so for the theory of electron transfer, we're going to focus on examples from the inorganic chemistry literature because it's a little bit easier to identify, let's say, a reaction coordinate in terms of a metal-ligand bond. In principle, you can do the same for organic system, but it's a little bit more complicated. And the idea here is for you to have sort of an introductory or conceptual understanding of how these things play out. So we will focus mostly on those. In electron transfer processes, there are two types of transition states. This was after the late Henry Taube, a Nobel Prize in 1983 for studies of an electron transfer. Actually, Henry Taube was a member of this department, but from here he went to Stanford. So there's two types of transition state, so-called inner sphere and outer sphere. So inner sphere involves a bridge between the reactants in the transition state. Okay, a bridge between reactants in the transition state. It means that the nature of the transition state has very close coupling between the reaction partners. On the other hand, outer sphere can be considered as the exchange of an electron between two spheres. So imagine two spheres coming across, electron jumps, and everybody goes their merry ways. So a much lower level of interaction. So if we look at outer sphere electron transfer. So here we're looking at the reaction of tris bipyryl ruthenium-3 and tris bipyryl iron-2. This species is more than capable of oxidizing the iron-2. So this would be in equilibrium with ruthenium-2, which is the reduced form, and iron-3, which is the oxidized form. So how do we imagine this taking place? So you have the two reactant partners, the ruthenium-3 and the iron-2. They form an association complex, and there's an equilibrium constant associated with this, and that's why we put the little brackets here to reflect that, you know, this is an entity usually separated by some solvent sphere. So within this reaction partners, electron can exchange. And so the electron goes from the iron-2 to ruthenium-3. So this guy is reducing that guy. So this goes from iron-2 to iron-3. This goes from ruthenium-3 to ruthenium-2. And so the net reaction, basically, once you have that electron transfer having taken place, then these things dissociate and you end up with tris BP ruthenium-2, meaning the reduced form and the oxidized form of the iron. And the K observed, the rate that you observe, this K observed, will be equal to the rate of electron transfer, which is the rate determining step here, and this K association, or the association constant. At an electrode surface, you can think of it as having tris bipyridine ruthenium-3 and the electrode providing the electron to give you tris bipyridine ruthenium-2. In an inner sphere electron transfer, this is a really famous experiment by Myers and Taube. So here we have hexaquochromium-2 and penamine cobalt chloride 3. So this guy and that guy. This is beautiful blue complex. This is not that colored. And the net result is that you end up with the pentaquochloro and hexaquocobalt. Okay? So we go from hexaquochromium to pentaquochloro. You go from penamine chloro to hexaquo. So clearly a lot of moving parts here. The first thing that is clear is that the coordination environments between reactants or products are very different. More frequently than not, that tends to imply an inner sphere electron transfer mechanism, although not necessarily. So how do we foresee this process taking place? So we have the hexaquochromium-2 with the penamine chlorocobalt 3. As before, we have this pre-association. So this key association making this reaction partners. And then the real T-step is this one. So what we have within that system, the chloride moves to become a bridge between the chromium and the cobalt. In the process, it displaces 1 mole of water. So the reaction here is chloride gets closer to the chromium, 1 mole of water comes out. Now you have a bridge between the chromium and the cobalt mediated by the chloride. Once that takes place, now you can have electron transfer from the chromium to the cobalt. So the chromium goes from chromium 2 to chromium 3, cobalt goes from cobalt 3 to cobalt 2. And that's a K electron transfer. And then there's a series of very fast reactions where all hell breaks loose. But now you have that the chloride then gets transferred over to the chromium. And then in rapid sequence, because this is cobalt 2, it's substitutionally very labile, all of the amines come off, and you end up with hexaquo cobalt 2 and the chromium pentaquo chloro. And so a couple of things. One, reactants or products are very different. And so you need to take into account, that aspect, and also the fact that in order for this process to be inner sphere, you needed a bridge between the reaction partners, mainly between the chromium and the cobalt, and the chloride as a bridging ligand provides for that. And so now the observed rate is K1, which is this pre-association, K2, the formation of the bridge, and then K3, which is the electron transfer event. And so these are fundamentally very different processes. In one case, in the previous one, if we go back here, it was like two spheres coming together, electrons get a change, everybody goes their merry way. The ruthenium and the iron maintain their coordination geometries. In this case, you start with hexaquo chromium 2 and penamine chloro cobalt 3. Upon electron transfer, you end up with chromium pentaquo chloro, chromium 3, and hexaquo cobalt 2. The beauty of this experiment, and it's one of the nicest, this was in the 50s where, instrumentation was like a spectrophotometer and a battery. But the design is, what's really amazing. There's no other way that you can get those products without having an intermediate that is sharing the chloride as a bridging ligand, because you have the net transfer of the chloride from this guy to this guy. As you can see, the chloride goes from the cobalt to the chromium. And so that was probably the first clear experimental observation. And there's no other way to interpret this. And I think that's the beauty of this experiment. And so it could establish that the mechanism of the electron transfer involved intimate interactions between reaction partners. And then, this gave rise to all sorts of different, you can imagine, changing the chloride to bromide and iodine and all this other stuff, coming up with different ligands. The critical distinction here is that the transition state in an inner sphere involves a bridge between reaction partners. Whether the coordination environment changes in the end is not necessary, but it's often the case, because you're talking about generating substitutionary labile species by the simple event of the electron transfer event itself. If we were looking at an equivalent electron transfer event in an electrochemical interface, so for example, the reduction of chromium, the oxidation of chromium 2 to chromium 3 can be mediated by an adsorbed layer of chloride. So chloride here becomes the bridging ligand between one of the reaction partners, which is the electrode surface, and the chromium itself. There are other ones. So for example, tetraiodo-cadmium. So this is cadmium I4. On a mercury surface, it absorbs with two iodides, basically contacting the mercury surface, bring the cadmium to the inner part of the interface. And so if we go back to this idea of outer sphere electron transfer, if we think of a self-exchange rate, and so here in a self-exchange means that the reactants or products are the same. So for example, if you take a look at, we go back to the ruthenium 3 BP plus 3 plus 2, right? That's in equilibrium, let's say, root BP plus 2. Let's put a star here, meaning we can distinguish them, and root BP plus 3, right? This is a self-exchange process, meaning that reactants and products are the same. However, in the transition state, a number of things have to happen. The radius of the ruthenium-3 BP3 is smaller than the ruthenium-2 because of electrostatic constriction. And so to reach the transition state, the ruthenium-3 plus has to compress a little bit. The ruthenium-2 plus has to expand a little bit. Why is that? Because again, by Frank-Condon, there can be no changes in the nuclear coordinates during the electron transfer event. And so what that means is that for outer sphere electron transfer, in this case, the structure around the reaction partners will look like a 2.5 net oxidation state. And so both have the appropriate nuclear coordinates, the electron can exchange. And it's in this context that, let me see, in this context that we will talk about Marcus' theory of electron transfer, and what he would, his theory, in the classical limit, tells you how you reach the transition state. How do you get to that intersection region? By changes in the nuclear coordinate, changes in the polarization. The other thing that you will notice here is because the charge density on the 2 plus is smaller, the solvent dipoles are less polarized here than in here. So you're going to have to take into account changes in metal ligand bond distances, changes in the polarization of the solvent. And this will in turn contribute to the activation energy, which is at the heart of the Marcus theory, which in a real sense is sort of a classical theory, except put in terms that are tractable and that we can actually do something with them. Let's just stop here, and we'll pick it up again tomorrow. If there's any questions, now would be